The effect on the sea surface gets bigger and bigger.
Okay, so that's in the shallow water. Now, what about the 2004 quake? To get to the question here, if you'd been in a small boat directly above that one, what would you have felt?
Well, that's a good question. This is where the interest comes in here. It's because the displacements took place in 2,000 meters of water, so that a little boat sitting at the top of the fault wouldn't notice very much. And we can put this in perspective by thinking, those hydraulic lifts they have in garages. They put your car up and they lift it up. So imagine taking one of those kind of hydraulic lifts, putting a big plate on top of it, putting it at the bottom of a swimming pool, and lifting it up suddenly, say a half a meter, just to keep things in perspective. You can imagine what happened in a deep swimming pool. The water would sort of surge off to the side. There'd be displacement at the surface of the swimming pool, but most of the water would just go sideways, so there wouldn't be much of an effect. Now, take that same piston, that same contraption, and put it in a kid's wading pool and do the same thing, you can see there would be a massive displacement of the water. But we got to talk about the earthquake itself, because the earthquake, in addition to dislocating the seafloor in this case, also radiates out energy. 3 kinds of energy come out, and they propagate to the solid earth. First of all, there's the low-frequency Rayleigh waves. Those are the ripples that you see on the seafloor. And on the earth, we see those as undulations in the land. And there's also the higher-frequency elastic shear waves. But these can't propagate in water. So we're left with the pressure waves. And the pressure waves are compression waves that produce infrasound and large shock waves, acoustic shock waves in the ocean that propagate up to the surface.
So would you hear something if there's shock waves?
Yeah, this is the really interesting feature that I didn't know about. These shock waves propagate up from the earthquake. And they have this, they're like a shock wave from a jet plane going by, one of those sonic booms. And so ships at sea sitting over the earthquake would hear a thump or a bang. It's like somebody beating on the hull. And in other cases, it's such a shock and such a boom that sailors actually think that the ship's run aground or it's hit a rock or something. And this rumbling sound that sailors sometimes report in the vicinity of an earthquake is actually because the frequency of these acoustic shocks is about 10 to 20 hertz, which is right at the limit of acoustic hearing for human beings, young people at least.
That's astounding. So again, to get to Murray's question here, if they'd been over that earthquake, they wouldn't have felt anything in terms of the water going up and down much, but they would have heard a sonic, like a boom of some kind.
Yeah, but when you think about it, being at sea on a small boat on the Boxing Day 2004 earthquake would have probably been one of the safer places to be in the world.
Dr. Thompson, thank you very much.
You're very welcome. Thanks for having me.
Dr. Richard Thompson is a senior research scientist with the Institute of Ocean Sciences in Sydney, BC, which is part of Fisheries and Oceans Canada. This next question comes from Mick Shuchuk, who wants to know why a heavily panting dog doesn't hyperventilate. Waiting breathlessly with the answer is Dr. Lee Lamont from the Atlantic Veterinary College in Charlottetown, PEI. So, Dr. Lamont, what is hyperventilation and how does it happen to humans?
Well, the term hyperventilation means that a person or an animal is overbreathing. So in other words, when an individual hyperventilates, their rate of breathing and or their depth of breathing can be increased. Certainly in people, we see this syndrome most often when someone becomes stressed or anxious and is exhibiting a panic attack. And oftentimes then they develop symptoms like lightheadedness, dizziness, numbness of the extremities, and sometimes even loss of consciousness for short periods of time.
Now, is this because you're getting too much oxygen into your lungs?
Well, actually, what's happening is when someone hyperventilates, they are exhaling excessive amounts of the gas carbon dioxide. And when this happens, the blood level of carbon dioxide is also lowered at the same time. Now, under normal circumstances, the nervous system controls the rate and depth of breathing very precisely to assure that the level of carbon dioxide in the blood stays within a very narrow range. So when someone hyperventilates, they acutely lower this level of carbon dioxide, and the nervous system then responds by causing constriction of blood vessels supplying the brain, And what happens is we get decreased blood flow to the brain, decreased oxygen delivery, and that's what precipitates all of those symptoms that I just mentioned.
Oh, wow. So I've always thought it was too much oxygen, but it's actually too little carbon dioxide. That's
too little carbon dioxide. And paradoxically then, someone that is over-breathing can actually have decreased oxygen delivery to the brain.
Because the blood vessels are constricted.
Exactly.
Okay, so that's hyperventilation in us. How is panting in dogs different from that?
Well, panting is actually the major mechanism of thermoregulation in a number of animal species, not just dogs. And they do this then when they're exposed to heat stress or during exercise. So when a dog pants, then, they replace the warm, moist air in their nasal passages and mouth with fresh, dry air. And this then dramatically increases the process of evaporative heat loss. So when a dog pants, they may breathe at a rate of between 200 and 400 breaths per minute. So you can contrast this with a normal dog at rest who may only breathe 20 to 30 times per minute.
Holy smokes.
Yeah. So why don't the rate of breathing is dramatically increased.
Well, so why don't they hyperventilate then if they're breathing that fast?
Well, the key to panting then is even though the rate is increased, the volume that the dog moves with each breath is significantly decreased at the same time. So really the net effect on overall ventilation is minimal. And the blood level of carbon dioxide then, which is really key, is actually not changed from normal. And so there's no vasoconstriction of the blood vessels to the brain, and none of those symptoms that we talked about when we were talking about hyperventilation.
What you mean the dog is just breathing shallowly? So what's going on in the lungs?
Well, gas exchange actually is pretty minimally changed in a panting dog. So while their rate is increased, the volume of each breath is dramatically decreased, and the net effect is sort of a wash, and their levels of carbon dioxide and oxygen in the blood stay really within a normal range.
Oh, I see. So there's a lot of pants where there's just a little bit of air going back and forth.
Exactly.
So not much is going in and out of the lungs.
That's right.
Just take me through again, like what the panting is actually doing for the dog. How does this heat regulation work?
Sure. Well, it's all about evaporative heat loss. And so by rapidly increasing the rate of breathing, the blood flow that is then coming to the nasal passages and the mouth is being exposed to fresh, dry air, and that allows, through the process of evaporation, for dissipation of that heat. So it's actually quite an efficient process. It's interesting in panting as well. They've shown that blood flow to those areas, to the tongue and to the mouth and to the nasal passages, is increased by up to 7 times in a panting dog, and that just further increases the efficiency of the whole process.
Holy, so they're cooling their mouth and their tongue. It's not just the tongue hanging out to the side.
Exactly. And the net effect is to cool the blood overall throughout the whole body.
Is this in place of sweating?
Yeah, dogs don't really have sweat glands in the same way that human beings do, so they don't sweat to lose heat. So
the panting, really good for losing heat, but not affecting their brains because the breaths are so shallow.
Yeah, that's right.
Dr. Lamont, thank you very much.
Thank you very much.
Dr. Lee Lamont is a veterinary anesthesiologist from the Atlantic Veterinary College at the University of PEI in Charlottetown.
Elias in Quebec City. In the late evening, if you run your hand through seawater, bacteria in the water will often light up. Why do they do this?
To illuminate the answer, I'm joined by Dr. Richard Rivkin from Memorial University in St. John's, Newfoundland. So, first of all, Dr. Rivkin, is it actually bacteria that Keith is seeing flash when he runs his hand through the seawater at night?
Well, actually, the type of phenomenon which you've described is probably being caused by an alga of the class Dinoflagellates rather than bacteria. Bacteria are certainly bioluminescent. They produce light in a similar spectrum, similar color. But what is typically described and is typically seen when you're on a ship or in a bow wake or at a beach and the surf's breaking are other eukaryotic organisms rather than bacteria that produce light in flashes rather than as a continuous glow.
Oh, well, why are the algae doing that?
Well, that's a good question. There is a generally accepted hypothesis, which may or may not be correct, that the sharp production of light over a very short period of time is used as predator avoidance. It's been called a Proteus display, and it frightens the predator away. And it occurs in most xenoflagellates, not all, but especially the ones which are found in the upper ocean.
You would think that by flashing it would attract the predator and tell them where they are.
Well, they don't flash unless they are stimulated.
Oh.
They generally don't just glow, which is different than bacteria, because bacteria, when they're in very, very high abundances, produce a continuous glow of light. And it's a phenomenon which has been reported over the centuries from ship's logs in various areas of the oceans, primarily in the western Indian Ocean off the coast of Somalia and in the area around the Philippines and Java. And it's a term which has been called the Milky Sea phenomenon or Milky Ocean.
Wow.
And unlike the production of light by eukaryotic organisms such as dinoflagellates or ctenophores, the light is produced continuously and can occur for days on end.
So this is in the deep ocean then, as opposed to on a beach where you would see the algae with your hands. Is that correct?
That's correct.
Well, how do you know that the stuff in the deep ocean isn't algae instead of bacteria?
Well, that's a good question, and according to the reports, the type of bioluminescence and the continuous luminescence is something which does not occur in algae. It only occurs in bacteria, and occurs in bacteria at very high abundances. And this is one of the very remarkable characteristics of this. Bacteria can communicate with each other when they're in high enough abundances. It used to be called autoinduction. Now it's called quorum sensing, where bacteria are able to communicate to one another to turn on specific genes, which produces this bioluminescence.
Wow. So the algae then are producing a flash when they're disturbed by putting your hand in the water, and the bacteria produce a glow that lasts for a long time.
That's correct.
But you also mentioned that it's when the concentrations of the bacteria get up, it's like a form of communication?
It's a consequence of communication rather than a form of communication. And abundance of bacteria, as I said, must be very high, on the order of 10 to the 22nd number of bacteria.
10 to the 22nd, that's what, 100 billion?
It's a billion trillion.
I can't imagine that. And is this the same thing that we see in deep sea fish?
It's caused by the same type of organism. Bacteria occur on the surface as well as in the gut of many deep sea fish.
But you're saying that that's made by bacteria, not the fish itself.
That's correct.
It's still bacteria.
It's still bacteria.
Okay. So in the deep sea, it's bacteria. Along the shoreline, it's algae. But either way, it's a very beautiful sight if you ever see it.
That's right.
Dr. Rivkin, thank you very much.
You're welcome.
Dr. Richard Rivkin is a university research professor in the Ocean Sciences Center at Memorial University in St. John's, Newfoundland.